Okay, so we're going to expand upon our diagram of the interior of the Earth, this time specifically looking at the interactions of the mantle and the crust. So we're going to divide this white section that I've got left up here into two sections. A layer that we call the asthenosphere is actually this top section of the mantle that we've drawn already, but that's not where the mantle actually ends. We're going to add the uppermost part of the mantle, okay, which is actually part of the lithosphere. Now, lithos means rocks, so the lithosphere, we're going to use this really dark red. The lithosphere is actually part of or included with part of the crust because the crust is made up of rocks. So that's where the lithosphere gets its name. But the uppermost section of the mantle interacts with the crust. So that's why it's included in the lithosphere. Okay, and again, it's okay if our designations or our divisions of the circle don't line up just perfect with the circles we drew already, because these layers differ in thickness in different places. For example, the lithosphere, which includes the crust in this uppermost layer of the mantle beneath mountains, is incredibly thick, almost or up to 100 kilometers thick. But you can also think of places on the Earth where volcanoes are erupting, and that magma that they're erupting actually comes from this section of the mantle. So there's some places where you can think of the crust as being 0 kilometers thick, with no depth at all. You're going straight from the crust and into the mantle, which isn't really true, but it's an interesting way of thinking about it. Just a way of thinking about that the crust itself is incredibly thin, but the lithosphere includes this top part of the mantle. And the reason for this is not just that they interact, but that the lithosphere is fairly rigid. This uppermost section of the mantle is closer to a solid than the rest of the mantle. Remember, we talked about the mantle as being plastic in nature, not quite a solid, not quite a liquid, but it's the lithosphere section of the mantle which is the most solid. And then you've got the outermost crust, which is that just thin little layer right on top of everything that is rigid. It is made of rocks, which are solid. And unless those rocks melt or are put under great pressure, they're going to stay solid. Okay? They may be weathered and eroded and moved around, but they're going to stay solid. Not like the asthenosphere, which is just below the lithosphere. You can think of the mantle section that we drew earlier as divided into those three sections. The uppermost part of the mantle, which is part of the lithosphere, the asthenosphere, which the lithosphere slides around on and is part of why we have plate tectonics, and then the lowermost section of mantle called the mesosphere. You know, we talked about a little bit that the fact that the crust is very thin. It's about 0 to 100 kilometers thick, including that uppermost piece of mantle that we call the lithosphere. Then we've got the uppermost section of the mantle, the asthenosphere, which goes from about 100 to 350 kilometers down. And then the mesosphere, which is that 350 kilometers all the way down to the layer of the outer core, 2,885 kilometers down. The outer core, which is that 2,885 to about 5,135 kilometers deep, and then that's where the inner core happens. And the very center of the Earth is 6,371 kilometers deep. So when we talk about the crust, it's incredibly thin compared to the rest of the Earth. But our diagram's not to scale, so we can make the crust a little bit thicker so we can see these interactions. And we are going to label this diagram at the very end. We'll label all of these different parts. You can label your diagram at home or in class if you're watching this in class. And we're going to use a little bit of green and a little bit of black next to make the divisions of the crust. So you probably remember from learning about plate tectonics earlier in your scholarly career that the crust is divided into two types, the ocean crust and the continental crust. We'll start with the ocean crust. The ocean crust is incredibly thin compared to continental crust. So there's the ocean crust and continental crust, two types. The ocean crust is very dense. It's much more dense than the continental crust. We're going to draw it in black. Okay, so we're going to use black to draw the ocean crust over the lithosphere. Okay, so I'm just going to kind of randomly start my ocean crusts. They're really thin, so we're going to try to keep that layer of black pretty thin. Okay, so just start on the side here. Anywhere is fine. We're gonna stop and leave a little bit of white space, maybe about half a centimeter of white space. We'll come back to this here in a second, and then continue your ocean crust on from there. So we're gonna leave a little gap, and then keep going. All right. Go a little ways, then we'll stop, and that'll be the end of that section of ocean crust. Okay, let's do the same thing on the other side. Another thin layer of ocean crust. Again, it's okay if we don't stay in our lines. I'm going to leave another gap kind of next to the other one that we've got going on there on the other side. I'll leave a little white space. Keep going. Now the ocean crust is not only thinner than the continental crust, but it's made up of a different type of rock. The ocean crust is actually made of igneous rocks, okay, rocks that come from a volcano, called basalt. Now there's some sedimentary rocks on top, but the major section of oceanic crust has basalt as its base. And basalt's the same kind of lava or igneous rock that the Hawaiian Islands are made of. They have basaltic rock pouring out of them. Okay, there's also other places around the world that have basaltic lava flows. Iceland has a lot of basaltic lava, flows up out of great cracks in the earth, which we're going to talk about in a little while. And it pours out this very dark, very dense, what geologists call mafic rock, basalt. Now, let's talk about the continental crust. Continental crust is much thicker than the ocean crust. And we're going to make the continental crust green because why not? Plants live on the continents. We'll just use green for that reason. Okay, now the continental crust is much thicker than the ocean crust. And you see that we're doing that in the diagram. Okay, always going to be thicker. Let's move our continental crust up to about the very top of our circle, and we're going to leave a little white gap again. Those white gaps are going to be important here in a moment. Okay, so we're going to leave a little bit of a gap there between these two pieces. We're going to come down and meet our other ocean crust here. Now the continental crust not only is much thicker, but it's less dense. It's less dense than the ocean crust, and it's made up of a different type of rock. Again, it's igneous rock. It's made up of rocks that came out of volcanoes, but it's made mostly of granite. That's the base that the continental crust is made of. I'm gonna put some more continental crust down here on top. We're not going to leave a gap in it though. We're going to just go completely solid all the way around right here. So granite makes up the very base of most of the continents. And then on top of that, we've got weathering and erosion happening almost all the time. And we wind up with sedimentary rocks on top of it. Now, the oldest rocks ever recorded on Earth, the oldest minerals, I should say, that have ever been found on Earth, have been found in Australia. Australia rides along with a continental crust. Okay. All right, so we've got our basic crusts labeled out. We've got the thin ocean crust painted in, and we've got the thick continental crust. We're going to talk about a little bit of these features that's on this diagram, specifically where mountains might be. Okay, so let's look at right here, where there's an ocean to continental plate coming together. There's a little mountain on top of that. Okay, so anywhere there's ocean crust hitting the continental crust, we're going to make a little mountain. Okay, and we're going to talk about why those mountains are there in the later episode when we talk about the different types of plate boundaries. But we're going to go ahead and put mountains there. Okay, so mountains wherever ocean meets continent. Okay, and let's go ahead and put some mountains right here in the center of this big continent. Okay, and what happens with mountains? They get so big that they actually bulge the bottom of the continental plate down into the lithosphere. Okay, because it's real thick there. All right. And that's what happens when two continental plates collide. They build these giant mountains, and they also bulge down into the mantle in the lithosphere, down into the asthenosphere below that. All right. Now we're going to go back to our black and look at where the ocean crusts are hitting the continental crust. Remember I said that ocean crust is always more dense than continental crust. It's made of that mafic basaltic material, those basalt rocks that are much denser, much heavier than the continental plates, which are made of less dense granite. So whenever a ocean plate collides with a continental plate, it goes underneath because it's denser, it sinks. We call this process subduction. Okay, so anywhere where we've got the continental plate next to the ocean plate, we're going to draw a little black line going down into the Earth's diagram. All right, so I'm going to do that. A little bit here coming down, and here coming down. And we can also have ocean to ocean collisions, and one part of the ocean crust will always wind up subducting underneath another. Okay, this is because the oceanic plates are heavy and they're thin, so the continental plates push them down, and sometimes this interaction happens between ocean and ocean plates as well. Okay, now plate tectonics is this process where all of these continental and oceanic plates move around on the surface. And that has a mechanism related to that heat of the inner Earth. Remember I said that the inner and outer core are incredibly hot. Now that heat comes from leftover heat when the Earth formed 4.6 billion years ago, but also from radioactive elements inside the Earth. So uranium and other radioactive elements decay into other elements, and they throw pieces off of themselves as they do that. They'll throw off neutrons and protons and electrons until they decay into a stable element. For example, uranium will decay into lead. It becomes a completely different atom. In that process, all those pieces falling off of those radioactive elements interact with atoms that are around them, causing friction and heat. So the inside of the Earth is being kept hot by those processes. Okay, Now, the surface and the atmosphere is radiating heat out into space constantly. So eventually the Earth will cool down. And when the Earth cools down, the mantle is going to get more and more solid, eventually until it's a complete solid and plate tectonics will cease. Plate tectonics will stop. But as long as we have that heat, it's going to cause a current of heat moving up and through the mantle. So let's talk about that next. We are going to label and draw, okay, arrows which indicate convection currents. Okay, so underneath our little open holes that we left in the crust, those are going to be the points where convection reaches the surface. So we're going to draw a series of arrows that go straight up from the top, or from the middle, rather, straight up from the outer core to those open spots. Okay, because heat rises as the outer core heats up the mantle, that changes the density of the rocks there in the mesosphere, and they begin to rise. Just like a hot air balloon rises because the air inside the balloon is being heated, the rocks do the same thing. Okay, we don't normally think of rocks as being able to be moved and heated, but again, remember that the mantle is not really a solid. It's not really a liquid either, though. It's plastic in nature, which is a in-between state of matter. It's not quite a solid, not quite a liquid. It's more solid than we would think of a liquid, but it can move and flow and cause these currents. And these currents happen over millions and millions of years. Okay, it takes millions of years for the mantle to rise and fall. Okay, but just like in a hot air balloon or in boiling water, once the hot material gets to the top, it starts to cool down. And when things start to cool down, they start to sink. Okay, so this current makes these little circular shapes of materials, warming up, going to the top, and then cooling down and falling back to the center. So we're going to draw arrows indicating that. And where it starts to fall back down is where subduction zones occur. Now, geologists are not quite sure exactly how this process got started, but some of them have said that it's less the convection current and more the slab of ocean plates falling in to the mantle or being pulled down. They call that process slab pull. But it's a combination of both. Okay, these convection currents occur because of that heat transfer and the change in the density of the mantle rock, mantle material. Okay, so slab pull is just the ocean plate falling back down in. And what happens is it's dense, it's heavy, so once it starts to subduct, it's going to yank and pull on the rest of that continental, or the oceanic plate. Sorry, I get it wrong. The oceanic plate. Okay, so as it starts to fall in to the hot mantle, it's going to subduct and go down. Okay, so let's just finish our convection diagrams. We're not going to draw in all down here because we want to leave some space for our labels. But we are going to draw in the convection currents here. Now these convection currents happen all through the mantle. Okay? And it's where the convection currents rise up that we have brand new crust forming. Okay? These two plates, okay, up on the continent and there on those two ocean plates that we drew, they are being pulled apart. Probably due more to the slab pull, the subduction zone being pulled back in, than being pushed by this convection current. Okay, it's more likely that it's the slab pull pulling down on it, moving it through and down into the other layers. Okay, so let's go back to our red, because where these convection currents come to the surface and where these plates are pulled apart actually cause volcanic eruptions we call rift features, okay, where new crust is forming. Okay, so here we've got new crust forming on a continent, it's erupting out into these great fissure eruptions, and here we've got it under the ocean floor. Or sorry, under the ocean, on the ocean floor. So we call features where it's under the ocean a mid-ocean ridge. And up here, where it's on the continent, it's a rift valley. So Alfred Wegener, a German meteorologist, first proposed the idea of continental drift when he noticed that the continent edges seemed to fit together. Unfortunately, Wegener, being a meteorologist, was not taken seriously in the geologic community. But it was much, much later, after Wegener actually died, that ocean surveys using sonar found these features on the ocean floor. And it led credence to his theory that the continents and the plates are moving around. Plate tectonics, as we know it now, includes both oceanic plates and continental plates moving atop the asthenosphere, with that top section of mantle moving with those continental plates. All right. Now, there's different features along the surface too, like those rift valleys. Anytime that subduction is occurring, these ocean plates melt and bubbles of magma come back up, and that's what forms these mountains. Sometimes they're volcanoes erupting at the surface. Okay, so we're going to add a little red here. Sometimes the magma never goes all the way to the top, and it forms what we call intrusive igneous rocks, usually granites. All right. Okay, so we've got our little eruptions happening there. And where two ocean plates collide and one subducts, we get volcanoes over that as well. And they have a specific name in geology called an island arc. It's called an island arc because usually it follows the boundary of the plate in an arcing fashion, a really big broad bend. But a good example of these is the Aleutian Islands off the coast of Alaska. All right. So we've got island arcs, volcanic mountains where subduction is occurring, and subduction has these slabs being pulled down underneath the continents, remelting and recycling. Okay, so we're coming in and adding some final touches to the diagram, adding our oceans over top the ocean crust in blue. Now, some other hidden features that we didn't see until we used ocean sonar to find them were very, very deep ocean trenches, like the Mariana Trench. The Mariana Trench is the deepest place in the ocean, and it occurs where an oceanic plate is subducting down underneath a continental plate. And it's those places which have the deepest places in the ocean. All right, so this is our little island arc, so I'm going to leave the top exposed. I'm not going to cover it up. Okay, there's new islands like this forming all the time. There's some new ones forming at the end of the Aleutian Islands. The Galapagos Islands are volcanic island arcs as well. All right, so we're going to finish out our ocean here, and that completes all the colors of our diagram. So let's look at and label all of these different features. Okay, put my paints down. All right, so labeling our diagram. All right, let's make a note at the bottom that the green is the continental crust and that the black is our ocean crust. Okay? And those two types of crust and this dark red layer are all part of the lithosphere. Okay? The lithosphere is the uppermost part of the mantle, the ocean crust, and the continental crust. Below that, we have the asthenosphere. Kind of think of it as the middle layer of the mantle. The asthenosphere is what the lithosphere rides around on, and it's part of what causes plate tectonics. Below that, we have the lowermost section of the mantle called the mesosphere, and then the liquid outer core and the solid inner core. And that inner core is so solid because there's so much pressure pushing down on it. But the outer core is liquid still because it's really, really hot. Okay, the inner and outer core are really, really hot. And it's that heat which causes the mantle to rise and fall in these convection currents. So let's label one of these mantle convection. All right? And it's mantle convection which separates areas on the continents and the oceanic plates where they drive apart. We call a divergent plate boundary. Okay? And that's also where new crust is forming. And it forms under the ocean on mid-ocean ridges. Okay, so we can label these as divergent boundaries, mid-ocean ridges. And this one up here is a divergent boundary, but it's on the continent, so we call it a rift valley. One of the most famous rift valleys is through Iceland. Iceland has this nice big fissure eruption going on right down the middle of it, and it's two pieces of the continental plate there on Iceland being pulled apart with new basaltic lava forming in the center. So eventually Iceland's going to be ripped apart and new ocean floors forming in between that rift, and the Atlantic Ocean will settle in and fill in those pieces. Okay. Where we have plates converging, okay, those are called convergent boundaries. They're coming together. And where we have ocean plates going underneath, that's called subduction. All right, so those should be all the labels that we're going to put on this diagram. Specifically, the mechanical layers of the Earth, the lithosphere, asthenosphere, mesosphere, outer core and inner core. Two types of crust, ocean and continental, and then two types of boundaries. All right, the next segments, the next video episodes that we're going to do are going to zoom in on these interactions and talk about the three types of plate interactions. Both convergent, divergent, and one that we don't have pictured anywhere on this one, that's transform. Okay, so let's label our diagram. You go ahead and make sure you get all of yours labeled. We'll show those digitally on here so you can read them. Make sure you get yours copied down and tune in for the next episode.